So we take what we started in Calculus 1 and bring it to the next level. So integrals will become now used for a lot of applications. And applications start with the approximations, which is why we reviewed Riemann sums, and we'll got to do it a few times more. But at some point, when we're lucky, we can go beyond the approximations, beyond, say, Excel, as we did yesterday, approximating the area of a circle. And when we're lucky, we can actually carry out that computation all the way through, including the limit. Okay, so we don't do actual the limit, but rather rely entirely on the fundamental theorem of calculus. Okay, so that's what we were doing yesterday. So we took our circle. This is, strictly speaking, half circle. Upper half of the circle, represented by the graph of the function, square root of 1 minus x squared. We integrated between -1 and 1. Okay. As we know from Calculus 1, it is the result should be the area under the graph, the exact area, not just the approximate. The substitution that we tried initially failed, so the doesn't mean that there is something wrong with the substitution as you learned in Calculus 1. So look for compositions, break into composition into 2, find the first step, that's your new variable. That's what over here in the box with the way we did it. So we were able to carry out the substitution all the way through, which resulted in a function at the bottom, which was not easier than the original, so we had to abandon it. So all this work, with no single mistake made, was lost pretty much because, well, it just sometimes it works out. That's the challenge of integration over differentiation. Differentiation works every time. Okay, there are rules, and you can always follow them. And if you start with a function that looks elementary, in the end result will be through elementary steps and through those rules of differentiation, you got the answer. Not so with integrals. We did nothing wrong, and yet we did not get the answer. So that's the challenge of integration, which is works in reverse of differentiation, and that's you don't expect that to be easier, or we expect it to be harder, which is like a square reverses square root is more complicated. Or you take sine and arcsine. Arcsine, well, it can only be understood in terms of sine. Or the exponential function and what? Log, right. So once again, you can only understand log in terms of the exponential function, and then translate that language into that information to learn about logarithms. And the same here, we understand things about differentiation, and we try to use that information to learn about integrals, and it doesn't work out every time. So there was nothing wrong, like I said. The idea was right and usable elsewhere. And yet we failed to solve the problem. We did not fail to do substitution. It worked out fine, but we failed to finish the job, which was to finish the integral. Okay, so then it was just a bad luck, and trial and error is pretty much one of the biggest methods of integration is trial and error. Usually it is not too many methods that you can apply, but for one method, substitution, there are many substitutions that you can try. For example, look at this substitution. What I picked u equal 1 minus x squared. Can you think of any other? How about x squared? Just as good. There's nothing wrong with that substitution either. So it's seemingly simplifying the expression. The result would have been the same. Many substitutions you can try. You can try substitutions that have nothing to do with the function, and they actually might work out. And that's the example of trig substitution. Not this one. This one worked out. We go back to our function, and then we tried trig substitution. The idea of the trig substitution, the idea of trigonometry as applied to this kind of function is actually bigger, a more important idea than the actual integral, because recognizing that this has something to do with the circle, and therefore with trigonometry is the insight that was not obvious to begin with. and easy to overlook. But since it's a circle, we know that sine and cosine, it's a unit circle as a matter of fact, and we know that's where the trig functions come from. So either you look at that triangle over there, you get the x for every point, x, y, you either have the x on the x-axis or y on the y-axis, and one is cosine and the other one is sine. Okay, so that's the red triangle right there. That's what it is. So with that idea, once again, you cannot guarantee it's going to work out. You don't know. It's just an idea. But you certainly can notice at what point we started to feel optimistic. It is when we did this substitution over here, and we realized that over here, and we realized that we end up with sine. So that whole business of complex composition, square root of 1 minus x squared, we were able to turn it into sine. So yeah, indeed, this one will turn into that one. So there is no composition anymore. We do have a different variable, but at least it is one function. So the good news then, the composition it was at least for the time being is gone, and it was very satisfying simplification of our expression based entirely on the Pythagorean theory. Okay, so then we are still not finished. So we arrived to this place first. Sine squared t, once again, it's a composition. Fortunately, trig functions have multitude of, seems like hundreds of formulas that you might try to use to simplify them. They are all in the book. Apparently, they did not put the formulas on the cover, but rather actually there's extra pages there at the end with a bunch of formulas. Maybe it's just cheaper to print on actual pages than on. I think they like color coded those pages. So is that the right book? Stuart is. Yes. So the blue one is the answers, I think, and the formulas are marked with gray. You see it, right? Okay. So all the formulas that you might need, including geometry, trigonometry like this, formulas for differentiation, formulas for integration as well. Okay. So all of them are at the end, and not just a few pages. Okay. So we use this formula. The name for it is the double angle. I think that's the name of it. Double angle identity. And we go then from the square to a function that has a double angle. Double angle is something that we can handle easily because the substitution is so simple, and we did. So that's what calculus 1 substitution that we did, and that's a very important skill. And then we finally arrived. We did the simplification. We finished integration right here. We did the back substitution there. Okay, so that's hold on a second. This I don't think I did it right. Did I? Okay. Well, no, that's not right. Okay, let's. I think I'll use this opportunity to review something that is also important, and that is substitution in indefinite integrals. So do you remember anything about that? Substitution in indefinite integrals.
You could set the integrals in terms of the new variable that you chose.
Right. So what's missing part here is the limits, and then you are recomputing the limits for the new variable. So over here, let me make that clear. We have x from -1 to 1, okay? And now we ignored this part, as you can see, we continued on, we dropped these limits, and we continued on as we should, as we're supposed to, into this, doing indefinite integration. Okay, so all of this, because it's just in the way, only until we reach this point, then the limits are to be taken into account. And then there's a possibility either go all the way back to x, do one more back substitution, or go back to the integral and change the limits from x to t. Okay, so let's do that. Let me rewrite. I have my integral from negative x from negative 1 to x equal 1, square root 1 minus x squared dx. Through all these computations, we have arrived to the, well, there is no integral anymore. There is no integral anymore. Okay, so we have from negative 1/2 t plus 1/4 sine 2t. I don't care about c anymore because this is a definite integral. Okay, so what's missing here?
The evaluation part.
Right, okay. And now we need to, so on the left it's entirely in terms of x, on the right it is entirely in terms of t. So then the limits have to be also with respect to t. But the good news is because the answer, definite integral, produces a number at the end. So that number does not depend on how you got there. It is not dependent on x, nor on t. That's why such a transition is justified, and we don't have to do one more substitution. We just have to figure out the limits. And let's take another look at our picture of t and x. So this is y equals square root of x, 1 minus x squared. Okay, and at the same time, I have my point here. If this is x, x is equal to cosine t. Okay, so the beginning is x equal negative 1 over here, and t equal, what is t? So once again, carefully transforming limits for x into limits for t, rather than doing them simultaneously, because it is, you can notice that it's actually tempting to I don't know, maybe it's just me, but when we follow the circle, we follow it counterclockwise, and the starting point appears to be at 1, not at negative 1. Okay, but if we look at one value at a time, we don't really care about the curve anymore. We only care about the initial and the last position of the curve. Okay, so we start at x equal negative 1 and at x equal 1. And now, what are the corresponding values of t? So what is the value of t, which gives me cosine equal to negative 1? Yes. Right. Okay, and x is equal to, let me have that arrow over here. That's the transformation, and the other one for the upper limit. What is t? 0. Okay. That's it. So so now the problem is totally recast in terms of t, and all we have to do is just to substitute. Okay. So just from top to bottom. So it will be negative 1/2 0 plus 1/4 sine 2 0 minus. This is 2 times 0. And now I substitute pi, negative 1/2 pi plus 1/4 sine 2 times pi. Okay, so once again, trigonometry comes into play, just specific values. 0, 0, sine of 0, 0. Pi over 2, and 0 again. So as you can see, the answer is pi root, as planned, as expected. So once again, we take a moment to appreciate what we have accomplished, because it goes way back 2,000 years back, and for the humanity and for yourselves and everybody who lives, you remember that fact from middle school probably. So the radius, circle has area of pi r squared. So we were able to finally demonstrate that, to prove it, and the answer is exact, not approximate. Okay, so things that we want to learn from this is, well, one thing is probably just to review it. We could try to ask ourselves what happens if the radiuses are rather than 1. What difference would that make? So I don't want to write the whole thing from the beginning, so we will work hard to do this. And it would be, if it was typed, I would just would copy, paste it, and then made modifications of the formulas. But I could just as well use my pen and do the exact same thing. At least indicate what we could do if we face radius r, the circle of radius r. So instead of 1 over here is r. So what difference does it make?
Y equals square root of r minus x squared?
Yeah, r squared, that's right. So instead of y, I'll have r squared. I would have r squared there. Okay. What about the substitution? So once again, the radiuses are not 1 anymore. So the relation, but the relation geometrically, the picture will be exactly the same. Just think about the radius being r. So what's x?
Are you sure it's r squared?
Yes. That's right. R cosine of t. Why? Because the hypotenuse now is r. The radius is r. Hypotenuse is 1. R, not 1. So that side, the adjacent side, will be r times cosine of that angle. Okay. So the substitution then is different, depending on that extra term. We will have a different substitution. But the rest is exactly the same. You will notice that there won't be any difference. So I will have r squared. I will have r squared there. R squared will appear over here as well. Okay, because x is r cosine t. So instead of having cosine t, well, without the square just yet, we'll have r cosine t squared. Okay, I will have also r over here, because of the differentiation. And then the cancellation inside of the square root will still happen. And we will still end up with the sine t, except there will be an extra r here and r there. And that's where the r squared comes from. Okay? So, and then that's why everything works out, and the answer would be r pi over 2r squared. Okay, so once again, half of the circle, it doesn't matter what the radius is. The plan, the idea works out just as well in the exact same manner. Okay. So what else do we learn from here? Something that a lot more than just that. So we have a very narrow purpose to demonstrate that the circle has radius pi r squared. So we have, but the inside is interesting. One is, once again, let me go back and show that we did it in a slightly different way. The substitution from the one that you did in calculus 1, it is once again at the bottom over here. You can see the familiar substitution. which is given by, where's my, u is equal to, this is u is equal to 1 minus x squared. That's the substitution. So u is new, and x is old. So naturally, when you have compositions, you introduce, you have two functions composed together. One of the functions you choose to be 1 minus x squared to be the new variable, and so the new variable is visible right away. Okay, so the trig substitution is much more subtle, and it goes the opposite direction. So we express the old in terms of new, right? Where is it? Old, x is old, and t is new. So we're going in the opposite direction. The formula is the opposite direction, but the rest is exactly the same. It doesn't matter. So it's either going from x to t or for t to x. The idea of the substitution is the same. So you replace x with something that depends on t, or vice versa. The result will be the same. It's just more subtle. It's just more subtle. You cannot just tell what that substitution is from the decomposition. Okay, so let me the conclusion that we made previously. Let me write it out. Okay, maybe in a minute. There's another insight in this, and that is the nature of t. What is the meaning of t? The meaning of t is on this picture. T is in fact the angle. Okay, so we have different relations between x as a variable or t as a variable. So x as a variable is the x coordinate. That's it. But on the other hand, and then y depends on x. Okay, and then but we can also use t as our variable, which is the angle. So then your location might depend your y or something else might depend either on your x coordinate that gives you y, or it can depend on the angle with the x-axis. So t is just as good a variable as x, and it is the picture shows that the geometry is actually gives you a simplification of the algebra, right? So 1 minus x squared is in fact from this picture, whether you use it for integration or not. 1 minus x squared is sine t. Okay, so that's the idea that we're gonna utilize for specifically representing circles. And the angle as the variable is very good, but actually there is an even more profound idea here. What if t is not the angle? What if t is time? What if we're talking about motion, which is actually the original Newton's idea of looking at functions? He thought of them as motion. And t, not by coincidence, used t here to indicate time. So we are moving along the circle, and our location then within the circle is given by what? X is cosine t, y is equal to sine t. This is called the parameter curve, which we're gonna study the last third of the class. So representing curves that are not necessarily functions, graphs of functions, by means of a parameter curve. So parameter curve means that there is a third parameter. There are x and y, but there is also a third parameter that is usually understood as time, and then you can speak of motion. And in this particular case, the motion is circular. So you're literally moving like this. You're starting your trip at t equals 0 over here. Then you proceed on here, t is equal to pi over 2, and here t is equal to pi. So, So your trip around this half circle takes pi seconds. Full circle will take 2 pi seconds, and you can keep going on, and every 2 pi seconds you will make a full circle. Okay, so that's the only way really to study motion, which is of any complexity, whether it is celestial bodies or even an object thrown in the air. There is always x coordinate, there is y coordinate, might be z coordinate too, and then there is t, and everything depends on t. So your location depends on your x, y, z depend on t. Okay, so that certainly is something that we're gonna. It is just as important as everything else. So we have three parts, and they're pretty much equally important. Okay, so. So once again, everything comes together here with the parameter curves and the substitution, new type of substitution, and the only thing that we'll look into later as well, it is what kind of remains a whole, sort of, is what to do about what if I do want an antiderivative. And the back substitution really makes things quite unpleasant. So just think about it. If x is equal to cosine t, that's what I did at the end of the last class. T is equal to cosine t is equal to x. So this is in fact our cosine of x. T is our cosine of x. So then you have the combination of two functions, sine 2t and our cosine of x. So that certainly is not a function that is easy to handle, but it can be simplified. So we'll look into that later. But at this time, we'll just try to think of a way to summarize this. And this is the summary of trig substitution. There are three of them. Main substitution. At least the first two probably is worth remembering. So if you have you see a certain expression in the integrand, and then that should suggest to you a particular substitution. So this is what we had: 1 minus r squared minus x squared. So expression here that we might deal with, and there might be other expressions, but this is something that might be hard to get rid of without trig substitution. So, and the substitution here is, once again, x equal r cosine t. By the way, r sine t works just as well. Doesn't matter. Okay, so that's what we did. You can certainly repeat this computation with r equal 1. This is what we did. And then there is r squared plus x squared, assuming that r is positive. The substitution x is r tangent t. And this one is looks trickier. I just feel obligated to mention it, but it's really not that important in the sense that the complexity increases and the substitutions become more and more complicated. Ultimately, if you know what the substitution is, you can finish the job, but there's a bit of a challenge there. Okay, so this is what is it? It is what is a cheat sheet, or with the you can you look at what you're supposed to integrate and you don't know what to do. At this time we have only one method to solve the problem, and that's a substitution. So then the question becomes, what substitution do I do? And frequently, even though this is a composition, you, however, don't probably will fail. It is possible just as well to fail with the substitution of u substitution as we have. U is equal to r squared minus x squared might fail. So ahead of time, you cannot tell whether it does or will not fail. As you remember, the function was slightly different yesterday, and when we had an x in front of that expression, and it worked out just fine. But if that straightforward substitution doesn't work, then try trig substitution. Which one? That's what. Okay, so if you have r squared minus x squared, it is about the circle, and the substitution is cosine. But there are others, and that is the r squared plus x squared. They suggest tangent. And we're gonna do what we're gonna do next.